These are the notes for AP Calculus on the topic of real-world rate of change problems. The first example says the rate at which people enter the Fresno Fair on a given day is modeled by the function E, defined by E of t. And the rate at which people will leave the Fresno Fair on the same day is modeled by the function L, defined by L of t. Both E of t and L of t are measured in people per hour, and t is measured in hours after midnight. These functions are valid between 9 a.m. and 11 p.m., the hours when the Fresno Fair is open. At 9 a.m. there are already 300 employees in the Fresno Fairgrounds. So since it says t is measured in hours after midnight, that means midnight corresponds to time 0. And that would be 9 a.m., which corresponds to 9 hours after midnight. So t equals 9. And 11 p.m., well, noon would be 12 hours after midnight, and so this is 12 plus 11 more gives you 23. So 11 p.m. corresponds to t equals 23. So then part A asks, how many people have entered the Fresno Fair from 9 a.m., which we figured out as t equals 9, to 6 p.m. So that's 6 hours after noon, so noon is 12 plus 6 gives you 18. Round your answer to the nearest person. So we're just looking at the people, how many people have entered. So the way we'd set this up here is to get from our rates, which notice the units are in, both measured in people per hour, back to people, we have to integrate. These are both the rates, or derivatives. So we integrate it from 9 to 18. And here we just want to know how many people have entered, so we would only use E of t, because that's the rate at which people enter the Fresno Fair. And here's where we use our graphing calculators to figure this out. So let's go ahead and do that. So I'll first show you on the TI-84 here. So if we go to y equals, let's enter in E of t, which is 16,000 divided by, and it's divided by 3 terms there, so make sure you put an open parentheses. And the variable in our problem is t. Notice this button x, t, theta, and this is for whatever variable you're using. It's just going to look like x, but it's the same function. So x squared, just a different letter, minus 24 t, which is x, and then plus 160. And then close parentheses. And while we're at it, let's go ahead and enter in L of t, which we don't need on part A, but we'll need on later parts. So that's 10,000 divided by parentheses t squared or x squared, again open parentheses, minus the 38x plus 370. And then let's change our window size also. Notice here it says the functions are only valid between 9 a.m. and 11 p.m., the hours when the fair is open. So our x minimum will make 9 and the x maximum 23, because the functions are only valid on that interval. And then the y min and max, notice if I graph it right now with negative 10 to 10, I don't see anything. So when you don't see anything, that usually means your window size is either too big or too small. In this case, too small. If you look at the numbers in our equations, you can see probably going to get some big values here. So for a window size, let's just try out. Let's try negative, say 10,000 to positive 10,000. See if now we can see them. There's the first one. There's the second one. So now we can see our window size is too big because we can barely see these at all. So it doesn't need to be that big. So let's try maybe 1,000 to negative 1,000 to 1,000. There we go. Now we see the first one pretty well there. And the second one. So maybe we want to make it a little higher on the Y max just so we can see that maybe 1,200. So we can see that second one just a little bit better. So it doesn't go off the screen. There we go. Okay, so now we have a picture of both of those. And we've got our window size accurate. So now we can just go quit out of here. And to integrate, go math. Number 9, function integrate. And we're integrating E of t, which was our y1. So variables, y1. And then comma, the variable is x, comma, lower limit 9, comma, upper limit 18. And we get 6,505.179. Now normally it would be accurate to 3 decimal places, but we're dealing with people here, and it says round to the nearest person. We can't have a decimal per person like we can other things that we measure. So we wouldn't round up here, so it would be 6,505 people. Now let's go ahead and look at the, since we looked at the 84, let's look at the Inspire and see how we can do the same thing on our Inspire calculator. So let's create a new document here. Add the graphs first. Let's go enter them in. Now we can, in Inspire, we can put it in as a fraction here. So it'll look more like it looks on paper. 16,000. And then, since it's in this form, we don't have to put the parentheses on the Inspire. X squared. Again, we're going to use x instead of t. Here on the Inspire, you can use x, y, or z, but we'll just use x here. Minus 24x plus 160. Enter. And then, oops. Let's enter in for F2. 10,000. Oops. Let's go ahead and put the fraction there first. 10,000 divided by x squared minus 38x plus 370. So again, we don't see them, so let's change our window size. On the Inspire, you go to Menu, Window Zoom. Normally we'd play around with it, but we already figured out the window size we needed on the first one. So the x minimum should be 9. That's when the fur opens. X maximum 23. That's when it closes. And the y minimum, I think we had a negative 1,000. And y maximum 1,200. Okay. And there's our graphs. And again, now to do the integral, document, insert, calculator, and the definite integral from 9 to 18, and it was our F1 of x we were integrating, because that was the rate people were entering. And you can see that you get the same answer, 6,505 rounded to the nearest person. Alright, let's take a look at part B now. Part B sounds like the same question, but if you read it carefully, it's not. It says, how many people are in the Fresno Fairgrounds at 6 p.m.? Again, round your answer to the nearest person. So the key difference here is we're not just looking at the people who are entering, because we want to know how many people are in the Fresno Fairgrounds. We also have to count for the people that are leaving, which is the rate is given by L of t. And We also have to account for the initial amount of people, which it says right here. At 9 a.m., there are already 300 employees in the Fresno Fairground. So, this is one of those initial plus change problems. The initial amount of people at 9 a.m. is 300. Plus change comes from the integral from, again, 9, initials at 9 a.m. opens, to 18. But this time, since we want to know how many people are in the Fresno Fairgrounds, we have to account for them entering and leaving. So our overall derivative or rate of change would be the rate that's increasing it, which is the rate they're entering, EFT, minus the rate that's decreasing number of people, which is LFT, the rate people leave, and then times DT. So let's go ahead and work this out on both of our calculators. So again, I'll use the 84 first. So, oops. There we can go 300 plus math number 9, function integrate. This time we want y1 minus y2 in our integral, e of t minus LT, so y1 minus y2. And then comma, variable x, comma, lower limit 9, comma, upper limit 18. And then enter. And we see there's actually 3,613 people. Down to the nearest person. And now let's do the same thing on the Inspire. So on the Inspire, again, we can start with the initial 300 plus definite integral from 9 to 18. And again, we want e of t, which is f1 of x, minus L of t, which is f2 of x. And we still get 3,613 this way as well. All right, let's go on to the next part. So part C says if the Fresno Fair decides to charge $14 for admission until 6 p.m. and $9 for admission after 6 p.m., how much revenue will they generate on this day? So revenue, just how much money they're going to get from selling tickets. So it doesn't account for costs at all. So remember, profit is revenue minus cost. So $14, let's put in words first. So it's going to be $14 times the people who enter until 6 p.m. plus, it's going to be $9 times the people who enter after 6 p.m. So that would be 14. And then what will give us the number of people who enter until 6 p.m. would be the integral from opens at 9 to 6 p.m. is 18. And since we're just looking at people paying when they answer, they don't pay, there's no money exchanged when they leave, so it would just be EFT, not EFT minus LFT. Because if you put EFT minus LFT, what that would mean is that people would be getting their money back as they leave, which might be nice, but it's not going to happen in reality. So 9 times, and 12 people who enter after 6 p.m. would be starting at 18, which is 6 p.m. And remember, the park closes at 11, which is 23. Equals 23, 11 p.m. And again, they just pay, they enter, so just EFT. So you have 14 times, that integral might look familiar because we already worked it out in part A, that was 6,505. And again, we're going to round it to the nearest person, because part of a person doesn't pay part of the admission. So 6,505. And then this one we haven't worked out yet. So let's go ahead and work this out in our calculator. Let's look at the 84 first again. So it's going to be the integral of just EFT, so just y1, comma, x is our variable, comma, the lower limit is 18, comma, the upper limit 23. And again, we're going to round to the nearest person here. So this one rounds up to 957 people. And then we can work that out on our calculator. 14. Your calculator knows the order of operations here, so we put it in like this, and then plus 9 times 957. We get $99,683. Be the revenue they generated that day. And we can do the same thing using the Inspire. So that integral would be from 18 to 23, and just f1 of x dx. And see, we get the same thing, 957. Okay, let's look at the next part. Part D says, is the number of the people at the fair increasing or decreasing at t equals 7 p.m. So 7 p.m. is 7 hours afternoon. So 12 plus 7, now corresponding to t equals 19. So now we're looking at one specific time, if the number of people in the fair is increasing or decreasing. So what you need is a derivative of the number of people in the fair, which the overall derivative is E of t minus L of t. That accounts for the rate people are entering and leaving. We just want at one specific time, so really all we need to calculate is E of 19 minus L of 19. That'll give us a derivative right at that time. So the way to do this on the 84, you just go to y equals I'm going to de-highlight these two, so they're still in our calculator but not active. And then for y3, I'm going to enter in y1 minus y2. And then what I can do once I have that highlighted is I can go second, calculate, and then value. The value gives you just the value when you plug in a specific x coordinate. So the value, in this case, we're going to plug in 19 once it finishes graphing that. See right here, it's negative 864.957. And since it's negative, since our derivative is negative at that time, we know the number of people in the fair is decreasing. So that's how we can explain our answer. So I can say, like this, at 7 p.m., the number of people at the fair is decreasing. And then the justification or explanation here would be since E of 19 minus L of 19 is less than 0. Alright, so if we got a positive answer, we would know if the verb is positive, the number of people in the variable would be increasing. So let's see how we can do the same thing on the spire. So I'm going to go back to the graph and then tab. Let's enter for F3. Oops. So let's go up to the other two. And this could be a check mark like on mine, or some of the inspires have an eyeball that you cross out. I'm going to de-check it here. That means it's still in the calculator, but it's not going to graph it. And same thing here. Cross out the eyeball or uncheck the box. And then for F3, I'm going to enter in F1 of x minus F2 of x. Okay, so now it's graphing. This is our overall derivative graphs here. And then if I go to the other part here, this one, all you have to do is we have in there's F3, the F3 of 19. Or I could go F1 of 19 minus F2 of 19. That would give you the same thing. And you can see we get the same answer on the inspire. All right, let's take a look at the next part. Question. Part E says, what is the average rate of people entering the Fresno Fairgrounds from 4 p.m. until 7 p.m.? So 4 p.m. corresponds to 4 hours afternoon, so that'd be T equals 12 plus 4, 16, and 7 p.m., 12 plus 7, 19. T equals 16 and T equals 19. It says the average rate of people entering the Fresno. So whenever you see the average of some function on some interval, the first thing we need is the 1 over the width of your interval, b minus a, so that'd be 19 minus 16. And then times the integral from 16 to 19. And then right here you put whatever you're finding the average of. Goes inside the integral. In this case, what we find the average is the rate people are entering the Fresno Fairgrounds. If it's just the rate of people entering, it would just be E of t. And we can use our calculator to work this out. Now notice this is an average, so on this one we will not need to round it to the nearest person, because you can have averages that are decimals. That's fine. So then I'm going to go math. So actually, so don't forget this is like a 1/3 out in front. I'm just going to go 1/3 in parentheses times, and then math function integrate. Just E of t, so just y1, comma, lower limit 16, sorry, whoops, x first, and then comma, lower limit 16, comma, upper limit 19, and we get 355.002. You can either round it off, round it up to 3, or truncate it at 2. Either way is acceptable on the AP test. And then the units, well, when you're doing the average of something, when you integrate E of t, that gives you people. Those are people per hour, but then this is back in per hour, so it stays the same units as this function. So you find the average of something, the units would need to be the same. So this would still be in people per hour. So the next question sounds almost identical, except there's one key difference. It's still the average, And the interval is still from 4 p.m. until 7 p.m. It's still from t equals 16 to t equals 19. But there's one key difference. This part's the same. Interval still from 16 to 19. What you're finding the average of is different. Here was the average of part E, the rate of people entering the Fresno fairgrounds. On part F, it's the rate of change of people in fairgrounds. So the whole rate of change, not just the rate of people entering. So now instead of just E of t, here's where you'd have E of t minus L of t. So now you want the overall rate of change. So we'll do these both on the Inspire as soon as I've done this one on the 84. On this one, you'd still have 1/3 out in front. Times math function integrate. This time it's E of t minus L of t inside of our integral, so it'd be y1 minus y2, comma lower limit x, comma the variable's x, comma the lower limit's 16, comma the upper limit's 19. And we get negative 517.662. Or 661 if you're trying to get it. Or you can write the whole thing out if you want. And again, the units, though, would be the same as E of t and L of t. It would stay the same when you're doing average, so it's still people per hour. Now let's do the same calculation using the Inspire for both of these. So for part A, you could just put the 1/3 on the outside. Times integral from 4 p.m., which was 16, to 7 p.m. 19, and the first one was just E of t, so that would just be f1 of x. So you get the same answer there. And the second one would be 1/3 on the outside. Whoops. Times, and I could have done this on the 84 as well, but I forgot. We already have in f1 minus f2 as our f3. So instead of going f1 minus f2, which I could do, it's already in there as f3, so that's what that's equal. So that would just save you a little bit of time. Could have done that on the 84 also, as y3. There we go, we get the same answers on the Inspire. All right, let's take a look at the next part. Part G says, at what time is the number of people in the Fresno fairgrounds a maximum? And since it doesn't specify whether it's talking about relative local maximums or absolute maximum, whenever it doesn't specify, it means an absolute. Round your answer to the nearest minute and justify your answer. So the first thing we have to do, whenever you're trying to minimize or maximize, in this case the number of people in the Fresno fairgrounds, you need its derivative. Well, we already have the overall derivative is E of t minus L of t. And once you find the derivative, you set it equal to 0. Do that on our calculator, and let's go ahead and look at the graph here. 84 first. You can see the graph. Here's the graph of our overall derivative, because remember we put this in as y3. So you can see, we'll draw ourselves a number line here. And for E of t minus L of t, our endpoints on this number line, when the part opens 9, when it closes 23, or actually in max. And then we look back at the graph real quick. What we'll be looking at, since this is the graph of the first derivative, whenever the graph is the same as what you're on your number line, we're just looking at the y values. So if we look back at our graph real quick, you can see the y values. And they start out positive until right there, where y value is 0, and then they're negative the rest of the way. So I'll just call that A. We don't know where it is yet. Well, we can see the derivative is positive until we get to A, where we get to A at 0, and then it's negative the rest of the way. Okay. So what this would show us is the number of people at the fair. Since the derivative of the number of people is positive, it would be increasing until we get to A, and then after A, it would be decreasing. So if we do a little sketch of that graph, it's increasing and then decreasing. So we can see at A right there, absolute maximum would have to be there. That's it. It's also a relative maximum. In this case, the endpoints can't be higher than that point. It's the shape of the graph. So we know it's A. Now to figure out where A is in our calculator, all we have to do, 84, we're looking for where this derivative is 0, which is already in as y3. So make sure y3 is the only one highlighted there. And then you go number 2, zeros. So then I'll ask you for the left bound. So using the left and right arrows, choose something to the left of the 0, hit enter. Let's see, it puts a little arrow there marking where you put it. And the right bound, choose something to the right of the 0, hit enter, you can see. And then your guess, just choose something in between there. Right there is our 0. And hit enter, and then I'll give it to you. Now notice this right here doesn't say 0, but it's really close to 0. This means 1.4 times 10 to the negative 10th is just scientific notation. So your calculator is giving you a very accurate approximation there of 15.81. So write it down on paper. Otherwise, no one else but you will know what your value for A was. And then store it in our calculator as well. So got store, and then so you can just quit and then store as alpha. So now it's in our calculator as A. Can do the same thing on the Inspire. Inspire, you just go to Menu, Analyze Graph, zeros, number 1, and then that's you the lower bound to the left of that 0, upper bound, and there it is, the same value. And then you can highlight it and then store variable. Whoops. Store variable, and then I'll just choose A again. You can move it around if you want to get out of the way. So then, since that has to be the highest place, we don't have to compare it with anything. The only thing is it's said to convert our answer to the nearest minute. So to do that, remember T is in terms of hours here. So 15 would be 15 hours after midnight, so that'd be 3 p.m. And to the nearest minute, we have to just convert the decimal part to minutes. This is in hours, you can just use the conversion factor. That there are 60 minutes in 1 hour. So if you multiply it by 60, this is in hours. You can see the units of hours would cancel out. And we'd be left in minutes. So if we take the decimal part, the easiest way to do that, we already have this as our answer. We can just subtract 15 from that to get the decimal part by itself, and then multiply by 60. And we get 49.15, so see it doesn't round up, so that'd be 49 minutes. So 3:49. Okay. So, and then justifiers, let's put it all together. We can say, let's do a statement, a number of people in the Fresno Fairgrounds is a maximum at 3:49 p.m. And to justify it, a couple things we can say. Since, well, first it happens at a relative max here, or local maximum. So what justifies that it's relative max? So it would be since our derivative, which is E of t minus L of t, changes from positive to negative at 3:49 p.m. And there's one other thing that's probably a good idea to mention, just so that you show you consider the endpoints. And you can say, and in this case our endpoints were 9 and 23. Either endpoints might as well specify 9 a.m. and 11 p.m. was a potential maximum. What they are is potential minimums. Okay, let's look at the next part. This one says, if h of t equals the integral from 9 to t of e of x minus L of x dx, using correct units, explain the meaning of h of 13 and h prime of 13. So, let's go ahead and find h of 13. The integral from 9 to 13, we just substitute 13 for t. E of x minus L of x. So you just have to interpret this, what this is. Notice that to change the variable e of x and L of x are the same as e of t and L of t, they just changed it to a different letter, just like we did in our calculator. That way, when you plug in 13, you don't plug the 13 in for the x's here, only for the t, which is our upper limit. So notice this is the overall derivative. So this represents, notice it doesn't have the initial of 300, so this is just the change without the initial. So we can say h of 13 is change, and the units are people, in people at the Fresno Fair. And we'd also need to specify from 9 is 9 a.m. to 13, it's 1 hour after 12, so 1 afternoon is 1 p.m. So that's what the meaning of h of 13 is. Now to get h prime of 13, well, before we can find h prime of 13, we need h prime of t. So let's go ahead and find that first. H prime of t means you have to take the derivative with respect to t of this whole integral here. And then just remember, when you have the derivative of an integral, remember that's where you use the second fundamental theorem of calculus, since those are inverse operations. Now Now let's see if it fits the second fundamental theorem of calculus exactly. Well, in order to fit, this has to be a constant, which 9 is a constant, and this is has to be the variable, which it does. And there's no chain rule involved here because it's just t. It's not 3t or t squared. And remember, all that happens then is the derivative and integral, since they're inverse operations, essentially cancel out, but when it changes, the variable changes to t. So that's equal to e of t minus l t. Another one that stays the same. And now let's see what happens when you plug in 13. This. So now, it's just at one specific time instead of a whole interval. And remember, this is our overall derivative, so it's very similar to a previous part we did. Look back at part D here. And we did E of 19 minus L of 19. That told us whether the number of people in the pair is increasing or decreasing. Because it was the overall rate of change at that one specific time. And that's what this one is also. So h prime of 13 is not the change, but the rate of change. In other words, the derivative. Change. And then the units here are in people per hour. At the Fresno Fair. Oops. At 13 is 1 p.m. So instead of over a whole interval, we're just talking about one specific time. All right, let's take a look at a different example problem now. This one says a gasoline tank at Chevron contains 5,000 gallons of gasoline at time 0. So it's like your initial amount. It doesn't give us a specific time what that corresponds to, midnight or whatever time, so we just don't need to know that. And then during the time interval 0 to 20 minutes, gasoline is pumped into the tank at a rate of WT, gallons per minute of the units. And during the same time interval, gasoline is removed from the tank at a rate of R of T, gallons per minute. So part A says write an expression G of T for the total gallons of gasoline in the tank at time T. So for G of T, we need to account for the initial amount, gasoline was in there, which was 5,000 gallons, plus the change, so it's another initial plus change problem, but this time we want it to work for any time t. So in order for that to work, well, the initial one starts at time 0, this time, and since we want it to work for any time to give us the change, instead of putting a specific number, we'll put the variable t there. That way, if you substitute in 4, the change from 0 to 4. If you substitute in 7, the change from 0 to 7, and so on. And since we want the overall change, the total gallons of gasoline here, we have to account for the rate that it's being pumped into the tank, which is increasing it, so WT would go first, minus the rate that it's being removed from the tank, which is R of T, so R of T, a second, all times T. Whoops. And there's one mistake I made here, let me just show you why. I actually don't want to call those T. The reason why is, if I call those T right there, then when I plugged in 4, this would be W of 4 and R of 4. We don't want to plug in specific numbers there, we just want the overall derivative. So you just have to change the variable. So something other than T, I'm just going to use X. Same functions, just different variables, so don't plug it in. And now this would give us an expression for the total gasoline, gallons of gasoline, tank at time T. The initial plus the change from 0 to whatever time we're looking for the amount of gasoline at. And part B says how many gallons of gasoline are in the tank at time 20. So now we can use the function we just got right here to find G of 20. So the initial 5,000 plus the change here, this would be integral from 0 set to 20 per t. And now you can see why we wouldn't want to put the 20 there and there, which is why we change the variables to x. So w of x minus r of x. Yes. So now we need to use our calculator for this part to work this out. So let's go ahead and enter both functions in. So I'll go ahead and clear out the other ones we have. And the rate it's entering W of t. Oops. Let's type that in there. So it's 195. And then open parentheses, because notice the whole sign is being squared there. So the sine of x over 4 and squared. And then for y2, the rate is being removed from the tank. That's 18, and open parentheses, because that whole cosine is being squared. So cosine, we'll just use x instead of t, x over 8 squared. Oops, I forgot another parentheses there. I want to square the whole cosine. And then this one has a plus 10 as well. And again for y3, I'll just go ahead and enter in y1 minus y2. And again, see the let's change our window size here. So the one we really need to see here is our overall derivative, y1 minus y2. So see if we graph it like this with the current window size, can't see it very well, can we? So the window size is all wrong here. On this one, for the window size, let's go ahead and change it. Notice it says these apply from 0 to 20. So x minimum would be 0, x maximum would be 20. That part we know for sure. And it looked like, based on our graph, the y min and max were much too big. So let's try negative 10 to 10. See if that's big enough. That's a little too small. See some of the graph, but not quite all of it. Let's add how about negative 200 to 200? There we go, so now we can see it. I noticed there's a 195 here, so that's why I chose 200. And it looks like we don't need to see so much down there, so just so we can see a little better, I'm going to make the y minimum 20 instead. Negative 20. There we go. So now we can see our graph pretty well. And let's go to main menu so I can quit. So it'd be 5,000 plus integral of w of x minus r of x, which we already put as y3. So we can do that instead of y1 minus y2, and then comma, variables x, lower limit 0, upper limit 20. Now here we're talking about gasoline, so you can have decimal parts. So notice it doesn't say round either, so 6,710.605. And the units here, it kind of gives it to you right here, but it is in gallons. As this was in gallons per hour, remember we integrated its gallons, added it to 5,000 gallons, the initial amount. Now let's do the same calculation on the Inspire. So I'm just going to open up a new document. I'm not going to save the other one. So add graphs. So let's go ahead and type in the first one, 195. Again, open parentheses. Sine of fraction there, x over 4. Actually put the squared on the outside so the whole sign gets squared, not just x over 4. And then for F2, 18 parentheses cosine of x over 8 squared, and then this one also has a plus 10. And again, let's change our window size. So menu, window, zoom, window settings. We already played around with these on the 84. So we know the x min and max has to be 0 to 20 because that's when these apply. And we figured out the y min. We did like negative 20. And y max was 200. Whoops. And let's go ahead and do one more thing. I forgot we entered in F3 already. So I'm going to go back and de-check these two, or deselect these. If you want to put a slash through the eyeball, you can do that. If you have your Inspire looks like that. And then F3, we'll put F1. Now it's not always the first one first. The only reason why it is because the rate that's increasing, whatever it is, goes first, which happens to be the first one we're given. That's the rate that gasoline is pumped into the tank, minus the rate that's being removed from the tank. Whichever the rate that decreases, whatever it is you're measuring, that one you subtract. Oops. There we go. And now I can insert calculator. And this was 5,000 plus definite integral from 0 to 20. This was F3, or you can do F1 minus F2, but this is a little less to type in, so. And you can see we get the same answer, 6,710.605. All right, let's take a look at the next part. This one says, is the amount of gasoline in the tank increasing or decreasing at time 12? So again, the way you do this is you look at the overall derivative, which was WT minus R of T, and we plug in one specific time, which is 12. So it'd be W 12 minus R. Okay. So again, on the calculator, the way you can do that, 8384. It would be, we already have it highlighted, I think. Yep, we do. So second calc, once you have that highlighted, value, and we want to find the value at 12. You can see right there, it's negative 6.207. The units here would be in gallons per minute. So again, notice it's negative is the key. So our derivative is negative there. So that means decreasing. So we can say gasoline tank is decreasing. T equals 12, and then to justify our answer, could say since W12 minus R12 is less than 0. And we can do the same calculation on the inspire. All you'd have to do here is go F3 of 12. All right, let's take a look at the next part. It says, at what time for 0 to 20 is the amount of gas in the tank on minimum? So again, when it doesn't specify, that minimum means absolute. Show the work that leads to your answer. So to find the minimum, what you'd have to do is first set the overall derivative, which was Wt minus Rt. Set the derivative equal to 0, and then we use our calculator to find that. So let's take a look at our graph here using the 84. Again, this is the graph of Wt minus Rt, so you can see it starts out negative, goes to positive, and then back down to negative and back to positive. If you want to see that a little better, I can make my y minimum a little smaller. Negative 50. There we go. So again, we draw our number line here. We can see, looking at the y values, it's negative, then positive, negative, and then positive. So there's Wt plus Rt. And this time our endpoints are 0 and 20. Those are what this stands for. So it starts off being negative for just a little bit until I'll call that A, where it's 0, and it's positive for a ways, until B, where again it's 0, negative for a little bit until C, 0, and then positive for us. So if we draw a little sketch again, what this will show us is where the gasoline in the tank is decreasing for a little bit, and increasing, and back to decreasing, and then back to increasing. So we draw a little sketch of what that looks like. Decreasing, increasing, decreasing, increasing. So if we're looking for the absolute minimum, there's a couple of candidates. One will be right here at that relative minimum, and then at A, and the other would be right there at the relative minimum at C. So let's go ahead and find A and C. Write those down. So using our calculator, again we'll use the zeros function. So the second calc for 2 zeros, left bound. If you don't want to keep holding on the left arrow here, you can just type in your guess. I'll type in 1 as my left bound, right bound over there, and then guess in between there. So A is 1.535. So 1.5353216. As long as you're accurate to at least 3 decimal points, that's fine, but keep it as accurate as possible in your calculator to keep your final answer as accurate as possible, as long as you write it down at least to 3 decimal places. And then let's find, well, let's store this first. Second quit, store alpha A. And then second calc, 2 zeros, left bound. This time I've got to be careful there, because I don't want it to go and find both of these, just want to find the other one here. So left bound right there, right bound right there, guess in between. So C is 13.491192. Store this in our calculator C. Now, to figure out which one actually is where the minimum occurs, we have to compare how much gasoline is in the tank at both of these times. And that's where we can use our function g of t that allows us to figure out the amount of gasoline at any time. So we can find g of a versus g of c. See which one is smaller. G of a would be 5,000, the initial amount, plus the integral from 0 to a. So w of x minus r of x dx versus g of c, again the initial amount 5,000, plus the integral from 0 to c, w of x minus r of x. So we'll be comparing how much gasoline is in the tank at both of these times. And again, we can use our calculator to do that. So we go 5,000 plus integral of, this was y3 on our calculator, comma x, comma lower limit 0. And if you store it in your calculator, you don't have to type it again. You can just go alpha a, it's the upper limit. And we get 4,971.623. And now let's compare that, see which one's lower, to g of c, which would be 5,000 plus integral of y3 again, comma x, comma lower limit 0, upper limit alpha c. And we can see it's not even close here, 5,980.317. And we can see this one is lower. So, what time it asks for the time? If it asks for the amount, it would be the 4,971.63. This is what time does that occur? So the time would be at t equals a, and the units for time here are minutes. And this is what it means by showing the look of these two answers. We showed our number line, we showed, or comparing those two. And then you can do the same thing on the Inspire. To find the zeros, remember, you just go graph and go menu, analyze graph, zeros, lower bound, upper bound. Let's store that as C. And then, sorry, oops, that was A. Sorry about that. Just do that again. I'll just click on this one again. I actually call that one C, so I can fix that. I can put store variable and call it A now. And then this one, store variable and call that one C. There we go. And let's look at the next part here. Now it says, what time is the amount of gasoline in the tank a maximum? So, if we look back at our number on the previous part, we can see the maximum could occur at 0, B, or 20, those three places. So let's compare those three. I don't have to do this whole thing again, we've already got them on here. So 0, B, and 20. So we need to find G of 0, G of B, versus G of 20. This time we're looking for which one of these is the largest. We already know G of 0, the initial amount is 5,000. And you could integrate from 0 to 0, but that wouldn't give you anything. G of b is the one we need to find. Plus the integral from 0 to b. W of x and r of x. So we'll have to calculate that one. And normally we do the same thing for 20, but remember in part A, we already calculated that, and that G of 20 was 6,710.605. So no need to do that again. What we do need to find is B. So using our calculator, let's find that last zero there. It's time left bound to the left of that zero, right bound to the right of it. Gets in between there. Get B is 11.641549. So write it down on paper, and then store it in your calculator. So I can quit, store alpha b, and then let's find what that equals. 5,000 plus integral, if we have this as y3 in our calculator, comma x, comma lower limit is 0, comma upper limit is b. And we get 5,992.603. So now we're looking for the maximum, or absolute maximum. So we can see the largest of these is at 20. And we show the left our answer. We did have to justify it. We could just say since G of 20 is greater than G of b, which is greater than G of 0. And it happens to occur in point in this case. Okay, let's take a look at the next part. It says, what is the average rate at which the amount of gas in the tank is changing? So again, there's that keyword average. And here's our interval from 3 to 14. So we start off with 1 over 14 minus 3. Times the integral from 3 to 14 of whatever you want the average of. In this case, it's the rate at which the amount of gas in the tank is changing. So it's the overall rate, so we need both WT minus the rate it's being removed, ROT. And then let's use our calculator to figure this out. So it's the TI-84 first. So 1 over 14 minus 3 is 1/11. Times integral of, we put that in as y3, comma x, comma lower limit's 3, upper limit's 14. That's 87.915. And the units are the same as WT and RT, because we find the average of that, which is in gallons per minute. And the last part says for T is greater than 20, so this is beyond the interval here we were previously looking at. Gasoline is no longer pumped into the tank. So since it's no longer pumped into the tank, that means that rate, this WT, no longer applies. But it does continue to be removed in the tank according to RFT. So RFT still applies. And K is the time at which the tank becomes empty. Right? But do not solve an expression involving an integral that can be used to find the value of K. So we just have to set it up when you see that right, but do not solve an expression. And it does involve an integral. So the way we can do this is to say, well, K is when it becomes empty. One of the easiest ways to say, okay, so the integral from, we're going from time 20 on. So the start at time 20 to K, that's when it becomes empty. And here, W of t doesn't apply, so it's just R of t dt. So basically, this integral would tell us how much gasoline is removed from the tank from 20 to when it becomes empty. So in order to make it become empty, the amount removed has to be how much was in there at time 20, which if you look back, we already figured that out. At time 20, there was 6,710.605. So when the amount removed from 20 to K is 6,710.605, the tank will be empty because that's how much gasoline was in the tank at time 20. And that concludes this on the topic of real-world rate of change formulas.